Hello, Dr. Mears and fellow classmates who will be watching this video presentation. My name is Matthew Seminar, and I am a senior studying mechanical engineering.
My name is Andrew Stahlheim, also a senior in mechanical engineering.
Our paper was titled The Thermodynamics of Internal Combustion Engines, Examples of Insights, and the corresponding paper number is below. So we decided to do our report, obviously, on internal combustion engines, and more specifically, 3 configurations that are tested throughout this paper. Their IC engines are commonly found in everyday life, and they're very well documented because of low cost, high power density, reasonable efficiencies. They correspond to most emission standards, and they run off readily available fossil fuels. As of now, they can provide us with continual operation with minimum needs to refuel. And currently, the main goals of internal combustion engines are increasing overall thermal efficiency along with an overall performance boost to the engine, but both are currently limited by the first and second laws of thermodynamics. And within the paper, there are 3 examples of IC engines: a low heat rejection engine, an exhaust gas dilution system, and an ideal Otto cycle.
To begin with, we'll do a quick overview of the first and second laws of thermodynamics. The first law describes how work and heat transfer are different forms of the same energy and have quantities that can be transferred between forms. For example, chemical energy being converted to thermal, then to mechanical energy in the case of an IC engine. For a control volume, for example, a piston cylinder device, the change in energy has to be equal to the inputs and outputs. The second law of thermodynamics was first brought about by Carnot, leading to the Carnot cycle. It will be used to determine the direction of the process, establish conditions of equilibrium, specify maximum possible performance of thermal systems, and identify the processes that are detrimental to the overall performance of the system. The most common statements used to describe the second law are the Kelvin-Planck and the Clausius statements. Last, the second law allows us to quantify the quality of energy through the concept of exergy.
So prior to the 3 tests, the paper just described general engine cycle simulation overall, which was a 4-stroke, 3-zone process that documented the basic combustion of an IC engine. So to test this, they needed multiple empirical submodels, and in figure right, it can be seen the black dashed lines show the control volume being examined with arrows in indicating heat transfer in and work out. To find these empirical submodels, multiple properties needed to be determined, and the working fluid was believed to obey the ideal gas model. The unburned mixture during compression is a mixture of air, fuel vapor, exhaust gas, recirculation, and residual gases. And the burned gases are determined by stoichiometry and equilibrium composition. Kinematic properties such as the cylinder bore, stroke, connecting rod length, and compression ratio help determine the instantaneous cylinder volume and surface area, where the combustion is found from equation 1 and 2 shown below, where XB is a mass fraction of fuel burned, A and M are constants, and Y is calculated from the crank angle, theta O, or start of combustion, and theta B, which is the duration of the combustion. Heat transfer is found using equation 3, where A is cylinder surface area, H is heat transfer coefficient, and T is temperature values. Mass flow rate is determined from the basic one-dimensional flow equation, and mechanical friction is present from rubbing, whether that be on the crankshaft, the bearings, the pistons, or the valve train. And there is pumping or auxiliaries such as oil and water pumps and the alternators. So the simulation was done on a 5.7 liter V8 engine. Properties of said engine can be seen in table 1 to the right, and the values used to simulate the engine are seen in table 2 directly below it. With an RPM of 2000, a brake mean effective pressure of 900 kilopascals, a compression ratio of 10, and a burn duration of 50 degrees CA. The fuel used was isooctane, and a large part of these internal combustion engines is the exergy destruction, which is being determined pretty much from the same equation that we have defined in class, shown in equation 4 below, with U being specific energy, V being specific volume, and S being specific entropy. And the O values are obviously determined at the dead state. The exergy of the fuel is found using equation 5, which uses Gibbs free energy, and the exergy destroyed is equation 6, which is finding a percentage of fuel exergy. The results are shown in figure 2. I'm not going to spend too much time reading off the numbers for you, but they can be seen easily in the figure. It's just important to note that exergy during the combustion process is highly irreversible. That's pretty much due to chemical reactions, heat transfer, and mixing that's associated with the combustion process. And extensive research has pretty much shown that uh, these unique results directly come from the second laws of thermodynamics, which is the quantification of exergy destruction during combustion, that it correlates with the temperature of combustion. And in certain conditions where the combustion temperature is higher, there is more fuel exergy preserved, but with lower combustion temperatures, less fuel exergy is preserved.
First model I will be discussing is the low heat rejection model. In the case of an actual IC engine, there is typically a large heat loss through the cylinder wall, cylinder head, and piston head that result in a lower efficiency. With the low heat rejection engine, an attempt is made to move towards adiabatic conditions by increasing the wall temperature to minimize heat loss during operation. To achieve this, a low conductivity material such as a ceramic is used. However, these materials are usually less durable than the traditional steel blocks. Another advantage is being able to remove the cooling system from the engine, therefore reducing the engine load. Last, the resulting increase in EGT would allow the efficiency of a turbocharger turbine to be increased. Figure 3 shows 450 Kelvin as a typical wall temperature, moving to 1500 Kelvin, which we will assume to be the gas temperature inside the cylinder, resulting in a net heat transfer of 0 during operation. Although the net heat transfer is 0, figure 4 shows that there is an instantaneous transfer, being that on the intake and compression stroke, there is energy transferred from the cylinder wall to the gas, and on the expansion and exhaust stroke, there is transfer from the gas to the cylinder wall. Between each case, the brake main effective pressure is held constant at 900 kilopascal, and from this, the increase in temperature results in both increased compression and expansion work through increased pressure, and the resulting efficiency change is better seen in the thermal efficiency because of this. Low heat rejection engines typically have a lower gamma, which result to less thermal energy being converted to work, which will be discussed further in the presentation. Figure 5 shows the energy distribution, describing that with the increased wall temperature, there is only about a 1.5% increase in the indicated work, while the heat transfer is reduced by about 16%. To begin looking at the reason for this, figure 6 shows that the available energy is only about 13.5% compared to the 16.5% energy through heat transfer. Additionally, the average EGT is increased, as mentioned before, therefore decreasing the volumetric efficiency from the less mass coming into the engine and the increased energy exiting through the exhaust. Last, the decrease in gamma has a negative effect on the cycle as well. For the low heat rejection engine, the assumption of 1500 degree Kelvin is fairly unrealistic, and therefore one might look at something more reasonable, such as 800 Kelvin, where the efficiency gain is only about 0.5%.
So the second example we have is an engine that was tested using or exhaust gas dilution, excuse me, also commonly known as exhaust gas recirculation, or EGR. And this method basically takes nitrogen oxide emissions from the engine, and it's a reduction technique that's used in a lot of gasoline and diesel engines. And it works by recirculating a portion of the engine's exhaust gas back into the cylinders of the engine by essentially using external piping to redirect exhaust gases to an inlet stream to be cooled. This method alters thermodynamic properties of the working fluids in the engine, causing concentrations of the inlet charge to change, and it also causes a decrease in the combustion temperatures. Both of these changes affect the ratio of specific heats and the thermal efficiency of the engine. The test results are shown on the next slide, and the test conditions that were used for a simulation. The parameters are just shown below in table 3. So all the plots show the percentage of exhaust gas recirculation on the x-axis and their respective tested variables on the y-axis. Figure 7 is exergy destroyed on the y-axis, figure 8 is heat transfer percentage, and figure 9 is thermal efficiencies. The first plot, figure 7, shows that an engine with diluted exhaust gases, there's an increase in exergy destroyed, and the engine that is using the adiabatic EGR has lower exergy destruction. That's just due to the fact that there is a temperature decrease from the cooling of the exhaust gases. So with the lower temperature, there's more exergy destroyed. And the second figure, figure 8, shows that with a cooled system, the heat transfer is decreasing because the temperature of the gas is decreasing from the engine. And with the adiabatic EGR, there is more heat transfer, obviously, because the temperature of the gas is increasing. In the final figure, figure 9, it can be seen that with an increase in exhaust gas recirculation percentage, the brake efficiency and overall net indicated efficiency, the percentages increase, while the adiabatic tested engine shows decrease in both the brake and thermal efficiencies. The results, a system using a cooled EGR shows improved performance results and a higher work output compared to the other two engines that were tested. One is the adiabatic test, the other is no EGR whatsoever, just your basic IC engine running. And the cooled EGR also shows the lowest amount of heat transfer and the highest amount of combustion, along with the lowest amount of net transfer out due to flow.
Next, I'll discuss the Otto cycle, which is one of several ideal standard models used to represent IC engines. The cycle is based on a constant volume heat addition to model the combustion process. Some of the assumptions include that the working fluid is air, compression and expansion processes are adiabatic and reversible. The combustion is replaced by a heat addition process. The exhaust blowdown is replaced by a heat rejection at bottom dead center, and that the intake and exhaust strokes are neglected. Making those assumptions will allow us to calculate an efficiency, but this efficiency is typically inconsistent with that of actual engines. Some pieces of the Otto cycle that are consistent with IC engines include that the compression expansion process, the temperature increase due to thermal energy addition, and the mechanical conversion of pressure to work. However, the Otto cycle is inconsistent in that it uses a heat addition process rather than a chemical conversion process, which would have irreversibilities from combustion. The cycle doesn't model heat transfer of the cylinder, combustion time in terms of crank angle, blow-by, incomplete combustion, chemical dissociation, or internal friction. Figure 11 shows the PV diagram of the Otto cycle with an isentropic compression and expansion and isochoric heat addition and rejection. Moving to figure 12, the effects of altering gamma can be seen through the expansion and compression work of a given compression ratio. The increase in gamma will increase the efficiency of the engine. Each of the compression work and expansion work equations are shown in figure 7 and 8 respectively, assuming a constant compression ratio. It's also worth noting that the increase in the compression ratio will typically allow the efficiency to be increased. To recap, we first looked at the laws of thermodynamics, then showing how they were used through a few examples. The importance of gamma was shown, and that increasing gamma will yield a better thermal efficiency. Then the low heat rejection engine that increased wall temperature to decrease heat loss and increase the thermal efficiency. We saw that there was little to no efficiency gained through this process, and that there were other obstacles such as the materials that would prevent the continual operation of such high temperatures. But the possibility for improved turbo applications was seen.
We saw with exhaust gas dilution that it just uses recirculated gases from the engine to cool the engine and improve the overall thermal efficiency and reduce heat transfer throughout the engine. A cooled EGR provides lower heat transfer and higher thermal efficiency, while the adiabatic EGR showed a higher heat transfer and lower overall thermal efficiency.
Last, we talked about the Otto cycle, which modeled the engine as a heat engine rather than a chemical conversion device. While there are some things that the Otto cycle models well, it does neglect combustion irreversibilities. One thing that it does do well is show the importance of gamma and the effects of the compression ratio on the engine. And with that, thank you for watching. If you have any questions, let us know.
Thank you.